between motion and static forces. And what Huygens proceeded to do with this particular result, first in 1659, then actually publishing fully in 1673, and now you can see these are two earlier slides that have been presented twice here before with Pat in the audience, and Pat giving me enormous encouragement to continue my work on both occasions. What Huygens did was to take this principle of centrifugal force, the tension in the string, and design a clock that happens to be a paraboloidal conical pendulum clock. The trick is to keep the center of the bob always on a paraboloid. If so, the period remains exactly the same no matter where the bob is on the period. It's a wonderful consequence of Newton's first two laws. He took that and built a clock, and with it measured the tendency to descend vertically. Specifically 15 Paris feet, 1.1 inches, that's half rg. So he's measuring surface gravity with an indirect measurement, presupposing what subsequently became Newton's two laws, and he's doing so to four significant figures, publishing it in 1673 with the details shown. And what he's done is take from Newton's, what we subsequently came to know as Newton's laws, he got a relationship between the strength of surface gravity, the lattice rectum of the paraboloid, and the period, and from those he deduced four significant figures, the value of G. He had actually done the same thing earlier in 1659, but didn't publish. By the way, where he published Horologium Oscillatoria, it's a fantastic book. It's the book Newton modeled the Principia. So it's quite significant to Newton. He had done it earlier in a rather clever way that he didn't describe very much. He gave the value. It's exactly the same value as the 15 Paris feet, 1.1 inches, Paris inches. The problem here is a conical pendulum that has to be kept at constant height. And so you need some sort of a servo mechanism to do it. Huygens has the clever mechanism of having a heavy chain hanging on the end of the string, and as the bob slows down from resistance effects, the weight pulls the string down, changing the tension and maintaining the constant height. You get the same result both ways. Both ways presuppose Newton's first two laws of motion. Newton himself tried to do the second measurement, wasn't clever enough to come up with a servo mechanism. He was less an engineer than Huygens, more of a mathematician and physicist than Huygens. But he managed to get within 1% of Huygens' known value, and then sort of abandoned it, struggling to maintain constant height. Okay, so what is this as evidence for Newton's first two laws? Well, what we end up with is two relations. One relation at the top, coming off of conical pendulum measurements of Huygens, that gives this limiting value of displacement over time squared as a constant times the tangent of the angle, where the constant is done two different ways: 2 pi squared times the height of the pendulum divided by period square, or pi squared times the lattice rectum of the pendulum divided by period square. On the other hand, statics has a totally parallel relation. The vertical tension is related to the tension necessary to maintain an angle, exactly by the same amount tangent of theta. So what we have here is two totally analogous formulas that correlate. Okay. Is that the only source of evidence? No. What's interesting, and this is the real evidence for Newton's laws, first two laws of motion at the time he published them, Huygens had an independent way of measuring the strength of surface gravity, totally independent of Newton's first two laws of motion. It's using a cycloidal or small arc circular pendulum. It presupposes Galilean gravity, uniform acceleration, and it presupposes pathwise independence. But it does not presuppose either of Newton's first two laws. It had already become, by the time of Newton's Principia, the standard way of measuring gravity, to such an extent that they were determining changes in the third and fourth significant figure from between Paris and the equator. So Huygens had provided an independent way of measuring the vertical tension which then from the formula, the second formula down there, gives you the tension Bk and the vertical tension. He had the numbers coming off of his conical pendulum measurements are exactly the same numbers once you multiply by mass. And therefore you could simply say, this is a direct measure of static forces, thanks to having the two independent ways of measuring the same thing. Okay, I'm almost to Pat's question now, not quite finished. So the striking thing here is what we've come to is an example in the 17th century of the same sort of thing we saw in the QED case. Converging measurements of exactly the same quantity using entirely different theoretical principles in the indirect measurements can be played off against one another to bring very powerful evidence to bear. And that's interesting and well worth studying, but that's not my topic for the moment. It's a topic I am working on. During a PhD oral last summer, the candidate, now Dr. Teru Mayaki, made an offhand remark, not terribly tied to his content of his dissertation, but certainly pertinent, that if all you have is an indirect measurement, a theory-mediated measurement, and the measurement is well behaved, that's automatically evidence for the theoretical principles involved, even if there's no other evidence for those theoretical principles whatsoever. Now, Pat is much too gracious to have jumped in and started challenging Dr. Mayaki in the middle of a doctoral dissertation defense. But what he did, he was sitting opposite me, and his eyes rolled to the ceiling, his eyebrows raised, and he started smiling. And I thought, is he going to challenge? But as I say, too gracious to challenge, but it was very clear he wanted to question that remark. So I'm taking that as your question that we didn't have a chance to discuss afterwards, and I'm going to answer it. I'm going to answer it for the specific case of Newton, because it's convenient for me to do so, having set it up. So what evidence, if any, would the well-behaved results from the conical pendulum measurements of gravity have provided for Newton's first two laws as of 1687 if there had been no other way to measure gravity? Then it's an open question just whether those conical pendulum measurements are measuring the hanging of an object vertically. So let me look at for two cases consecutively. Let's just drop out the simple pendulum measurement and look pure and simple at this correlation. Fine, we have the correlation, and that, I think Patrick would agree, is automatically enough to use the one to assign numbers, values to the other. But in doing so, all we have is a correlation, and that raises questions. Questions are about, could systematic errors in the measurement of one of those things be affecting the value in the other? Because they are not identically the same thing. They are two physically different quantities that are simply related by a correlation. And that's the kind of question Newton himself not only asked, he explored it at great length for the simple pendulum measurements, to concluding that Huygens' measurement required several corrections and had an upper bound on its limiting accuracy beyond the fourth significant figure. So that's a partial answer to Pat. Yes, there is evidence. Now let's take away the correlation. Say we didn't have a well-developed science of statics at all, and all we had were those conical pendulum measurements. Even that, and this was Mayaki's point at the time, even that is some sort of evidence for the laws of motion because they've just been tested. There's a consequence from them that a particular quantity in a conical pendulum properly constituted was going to be invariant. And it had proved to be invariant in two different configurations. If it had not been invariant, that would have been serious reason to question the two laws. But notice in this case, we have not even a correlation to work with. So all we're really able to say is prima facie evidence that what we're measuring here and calling force is the same as static force. And it then becomes a natural open question to ask, Is what we're measuring really the same thing as a static force? Just the fact that a string is involved in the conical pendulum doesn't guarantee that's the case. To give you the analog of that, is the Richter scale using a particular spike on a particular kind of seismometer really measuring the magnitude of earthquakes? And of course now, as we've learned since 1970, the answer is no. And that was the potential right here. The answer could have turned out no. So to conclude, Newton's Principia, he says at the very beginning, is an essay in a new way of developing evidence. The very first sentence on it, in the whole book, however, mentions measurement. And the more you know the book, the more you see that his whole new way of developing evidence turns on the well-behavedness of indirect measurements, time after time, quantity after quantity, all through the book. I started looking at the Principia in 1987, 25 years ago, and had the good fortune of already being very sensitized to issues about measurement. I had read the one volume that had appeared at the time of Foundations of Measurement while a graduate student sitting in a course by Frank Fisher on econometrics, and he recommended that book to me. And the last part of it is actually on derived measurements and measurements in physics, and it had a huge influence on me when I started reading the Principia, and probably did more than anything other than Maxwell's comments on the Principia to sensitize me to what's going on in the book. By pure chance, Pat was the last of these four authors I met face-to-face, that in 2007. But of the four of them, including Dave Krantz, with whom I was an undergraduate, Pat has been the one I've had by far the most discussions with. And I value those discussions over the last 5 years enormously. It's my chance today to express gratitude for that, because no one has encouraged me more with looking at measurement as evidence than Pat has. Happy birthday, Pat.